Hello. So let's continue today with just before I forgot how many of you was supposed to get this course as a doctoral course. You know, and there was also Artur.
Yeah.
And probably.
I think that there was somebody else that was sitting over here, but yeah, after me.
I told you, and I'll check. So if there is anyone else, and who is looking at this video, send me email. So I have to think about this. Okay, and then another message is that it seems that on Friday we cannot make a class, right? Even if I wanted to. So that's next. So today, next time, and next Wednesday. So we move to the next chapter. So essentially, what I'm doing, I'm picking up some information from the chapter. But if you're interested in the more details, just look for the book. So this book is quite detailed. So we will be talking about approximation theory. Approximation theory. Well, the goal is simple. So the goal is approximate a function. So in the basic case, it's a function of a real variable on the interval. With some variations. By some functions that you know, so by elementary functions. So you have function which is given, for example, by the measurement, for example, of some data, or just some function that you encounter in some study, and then you want to manipulate or to work with it. So you approximate it with elementary functions with which you know how to deal. So what's elementary functions is polynomials that we consider today. Can be some piecewise continuous function, or piecewise linear, for example, piecewise linear, trigonometric, etc. So some functions. So we start with basic fact. So let us consider the linear space. Linear space V. So that can be linear in algebraic sense. So it can be different thing. It can be just vector space, but it can be space of functions, for example, or space of fields, and so on. And we want to approximate some element of this space by an element of a finite dimensional subspace. W, so it's finite dimensional subspace. Okay, and subspace. So what means finite dimensional subspace? By definition, it means that you can have a basis. So you can find with a basis. So you can find a finite number of vectors which span the space. So it's W0, W1, Wn. So this is elements of this W, which means that dimension, in this case, we denoted dimension of this subspace is n plus 1. People in numeric like to start counting from 0, not from 1. Okay, so first is the theorem. I'll show you it exactly as in the book. So for norms space, linear space V, so assume that the space V has a norm, and by norm, using norm we can find a distance. So distance is norm of the difference of the two elements. So what we want to see is that for a norm to end given element F, there exists element P from W, which will be our, we'll call it best approximation in this theorem, best approximation, such that F minus P, the norm, is equal to minimum among all elements between F minus Q. Well, so essentially there are two messages here, that there is element P, which so that if you consider distance between given element and all element from your approximation space, it will attain minimum in some element. Yeah. In many cases, it's quite a trivial statement. So the only non-triviality is if you just really consider norm space. So the proof would be. So I'll give more or less the idea. So first, so there are two cases. So the first case is trivial. So the first case, if F belongs to W, then you just take P equal F, and norm of F minus P is 0. So it's minimum already. Norm is positive. So this is trivial. So now consider the case if F is not in W. So we want to approximate a point which is not in our subspace by the point from our subspace in the best way. So how you do it? Essentially, how you do it in this case, what you do, you consider the space, the linear subspace E, which is spanned, so it's all linear combination of the same vectors that were before. So it's original space plus the F. Right? So it's a linear subspace of dimension n plus 2. So we added one dimension. Okay. With the norm from original V. So you can take norm from V and just use it in E, right? So it's inside. So the next two steps is that consider consider infimum of what? Yeah. It's all not really necessary. Yeah, it's actually I think it was. Let's see. So consider infimum of this difference. Yeah, so it's not clear that we have minimum, but certainly we have infimum. And take, so it certainly exists, and take a sequence which realizes this value, such that so this is from definition. The sequence exists. So we have a sequence which realizes this value, but not necessarily converges. But this sequence is bounded in finite dimensional space. No? In V, which is essentially vector space, and which means that every bounded sequence has this convergent subsequence. So there exists a convergent subsequence. Which converges to, by definition, to some element in V. And by construction, so the difference will be exactly equal to this inf. But since it realizes at certain elements, so it's automatically mean. So infimum is attained at certain element. That's it. That's it. That's a bit too complicated because we assume that there is just norm. But in the usual situation, you have scalar product or inner product. Observation. So usually we have the inner product. So in the space, so often we have inner product, and if it's you have inner product, then finding the P is much simpler. So then if it's there is inner product, then this basis plus vector f give you n-dimensional n plus 2-dimensional vector space with the inner product, which is coming from here, and then the optimal approximation is just normal projection. So then P is orthogonal, is the orthogonal projection. So this, let's say, this vector space V, which can be arbitrarily large, and then we have subspace W, which is finite dimensional, and then we have point F that we want to approximate by the point in this W. So what happens is that the point P, which you approximate, is the one where you just project normally to this space, and this can be put explicitly. So explicitly, this construction works like this. So in this case, let W0, W1, and so on be orthonormal basis in W. So what it means that within the product, all vectors are orthogonal. So the scalar product is 0 when I and j are different, and it's 1. It's connected delta, so it's 0 when I and j are different, and it's 1 when they're the same. So it's orthonormal. So ortho means that they're 0, and normal means they're 1. Okay, in that case, what means projection? So in that case, again, so what you do is you can write F as projection of F plus orthogonal part. So you see this will be PF in this case, and this is QF. So it's F is PF plus QF. And how you define it, where P is the projector. The projector is defined as PF equals sum over all elements, and you just project them on and multiply. So this is a coordinate along this case direction multiplied by the case vector. And accordingly, the rest is the rest, right? So what you can check, so this is orthogonal projection. So what you can check that they are orthogonal. the orthogonal, and also check that PF is the best approximation. Of F on this space W. So somewhat quite simple and direct. Numerically, when you do from point of view of numerics, it means that whenever you have your space of functions, so you have some space where your functions leave V, you have space W where your approximation functions live. We will have an example soon. And if you want to find the best approximation, you need the orthogonal basis, and then you just use a formula. So finding orthogonal basis. Orthonormal basis. So for finding an orthonormal basis, there is a so-called the Gram-Schmidt process. So that's good for you to remember. It's very easy. We already considered it in some context. So Gram. So how we do? So what Gram-Schmidt process makes, it gives you the orthonormal basis from any basis. Having any basis. Of W, we define, so first vector we almost do not touch. So what we do, first vector you do touch. So what you do is, so you take as a first vector, so it will start with 0. U0 divided by its norm. Okay. And for the next, you take first you take UG for any index higher than 0. What you do is sequential for 1, 2, 3. Well, let's do just for the first. So for the first, what you do is we subtract component which is parallel to the previous one. So we subtract U1 W0 Okay, so what we did, we subtracted the component which was parallel to the previous vector. So now V1 is orthogonal to W0, and we just have to normalize it. Okay, and so on. So general formula will be that Vg is Ug minus sum from k from 0 to j minus 1, Uj wk, wk. So you subtract all components which are parallel to previous vector such that the resulting is orthogonal. all of them. Okay? So you see, so if you take scalar product of Vj with any w, any previous w, you will see that due to the orthonormality of these w's, it will give 0. And then normalize. So j is from 1 to n. So the theorem is that W0, W1 is Wn is orthonormal basis. So proof is an exercise for you. Essentially, you can just verify it directly. You just directly verify orthonormality conditions. You take scalar product, and using the relations, you just show that they are always 0 if they're different vectors, and it's 1 if the same vectors. Okay. That's simple. So important examples with which we will work. So consider V as the space of continuous functions on the interval from -1 to 1. Continuous functions on the interval from -1 to 1. And now, so W will be, so we will approximate continuous functions with polynomials. So polynomials mean that it's 1x, x squared, xn. So we want to approximate V by these functions, and then we have to define the scalar product. Scalar product here is just integral from -1 to 1 of the product. Right. And then norm is, of course, norm is the square root of f by f. Square root is it's one of the ways how you define everything. So let's just do the Gram-Schmidt process. So we start with the W0. So it's 1 divided by the norm of 1, the function 1. So what is a norm is it's 1 divided by norm is square root of the integral from -1 to 1 dx, which is square root of 2. So it's x is a constant. So it's first vector. So the next is, for the next we first have to find V1. V1 will be x, right? Minus what? So x minus x w, w0, w0. So what it is, W0 is, so it's x minus, so this is, so there will be square root of 2, which will give 1/2, right? And this will give integral from -1 to 1 dx. That's correct. Yeah. So this is, so how much we get? Yeah, so this is 0, right? So this is 0. So it's x. So it's x, and then we need to find the norm of v1, which will be square root of integral x squared dx. Correct? And this is x cubed over 3. From -1 to 1, this will be 2/3. So it's integral square root of 2/3. So what we get is that W1 is x over square root of 2/3. So far it's just prefactor. Let's just do the next one more. So V2 is x squared minus, with this formula, so minus, you should take x squared W0 minus x squared W1 which is x squared. So this is again 1/2 integral from -1 to 1 dx. Correct. And here we have this 2/3. So it would be minus 3/2. Switching to 3rd by x and by this integral. So it will be x squared by x cubed. Okay, x cubed, this integral will be 0, right? Yes. And this integral will give us 2/3, so it will be 1/3. Good. And then we also need a norm. So norm will be what? Will be square root of the integral from -1 to 1. X. This you can copy it by yourself. So this should be square root of 8/45. So that's a number. Which means that we found the next function is this. So, etc. So, and this way you find the sequence of polynomials which will be orthogonal to each other. So it will be orthogonal to each other. It will be orthonormal basis, and this basis it's what's called Legendre polynomials. So this sequence of polynomials is what's called Legendre Legendre polynomials, and then approximation of continuous function by Legendre polynomials with this scalar product becomes direct, because if you want to approximate the function with n polynomials, you just use the projector. So this you just use this expression. So you take these Legendre polynomials, and coefficients will be scalar products. So this is how it works. And the next example of orthonormal basis is also, so it's usually you do it on a space, let's say continuous function from minus p to pi, and then you take the space as a span, approximation space is a span of, and I already give you orthonormal basis, so it will be just the same, the same type of inner product, so it will be integral from minus pi to pi f of x j of x dx. So span from the following functions. So square root of 2 pi, so it's constant. It will be cosine of x divided by square root, sine x divided by square root, then cosine 2x divided by square root, sine 2x square root of pi, etc. So you can stop at any moment. So this will be orthonormal basis. So it's Fourier orthonormal basis. So this is Fourier orthonormal basis, which is approximation of any function or any continuous function on a periodic, on an interval 2 pi. So again, it's orthonormal, so you can expand it with a projector, and coefficients will be just scalar products, the integrals. So this is how it works. And there is, so the question is how good it can be, so whether it is enough to have this basis or not. So for example, there is a theorem which is called Weierstrass approximation theorem. We just tell that given any function f, which is continuous on an interval, and positive epsilon, there exists a polynomial of some order, so which we don't fix, so just polynomial such that the infinite norm between the two, so this is a norm in continuous in the space of continuous functions, so it's just simply minimum or maximum on this interval of the absolute value of the difference. And so this is infinity subnorm less than epsilon. So what they tell you that whatever continuous function you have, and interesting that it's continuous function, so it can be like this, right? You can always find a polynomial which is infinitely differentiable so that it comes as close as you want to this function. So the polynomial approximation works. So I will not give a proof. The proof, see the course of analysis. So it's classical theorem from functional analysis, and so it gives you that in principle polynomials are good to approximate, but there is a problem. So for the practical use, it is generally not very practical. And why? It's because the degree over the polynomial is often very large. For small epsilon. So usually we want to have computation which are very precise. So like take epsilon 10 minus 7, for example. And then it turns out that polynomial should be of degree 1 million. So this is certainly not practical, right? So that's why theoretically it works. Practically it's not so interesting. But this is where we start. So let's make 5 minutes break. Okay, so the next way to so the previous way to approximate the functions with polynomials was through the norm. So we use this infinity norm. So there is another way of approximating function is what's called Legendre interpolation. Or Lagrange. Well, so that's somewhat, the idea is different. So the idea is that you have a function as a function of one variable, and then you have some points. So x with 0, with 1, with 0, starting with 0. x0, x1, x2, until xn. And for these particular points, which are all different, so you know that there is a, you know the value. So it will be f0, f1, and let's take f2. So there are points, or some finite number of points given by on a graph of this function. So the idea is to find a polynomial which will pass through this point exactly, right? Maybe. So this will be p of x. Okay. So given distinct points, so all different on a real line, and values which already maybe not necessarily distinct. So the theorem tells you that there exists a unique interpolating polynomial of degree smaller or equal at most n. So n plus 1 points are given, so that means the degree is at most n, which is passing through all these points exactly, such that p of x j equal yj for all at all points. All right, so this Lagrange approximation, so you can uniquely define the polynomial of a given degree, so the given degree is not bigger than n, so one less than number of points, such that it's exactly passing through the point. The proof is elementary, but I think it's quite nice, so I'll give it. So the proof. The proof is given through the Lagrange basis. Lagrange basis. So Lagrange basis means that it's a basis of a function. So the function LK is a polynomial which is defined as a product of all points except point k. For point from 0 to n, taking all except point k, and you take a product of the ratio x minus xi divided by xk minus xi. So, and this you can do it for k, for all k. So this way you get a collection of n plus 1 polynomials, and these polynomials, so the polynomials, of course, degree, so these are polynomials of degree n, all of them. And they have the property that Lk computed at the point xj, well, it's delta kj. So it's 0, 1 k not j, 1 k equal j. Well, that's, you can see directly from the expression, right? So what you do, so the polynomial that we need is simple. So it is p of x is just a sum. It's just a linear combination of these Lagrange polynomials from Lagrange basis with the coefficients which are given by the values. Correct, no? So automatically, whenever you take xj, you give yj. So this is very limited. So we already prove existence, so what remains is uniqueness. The uniqueness is a bit more interesting. So assume that there is another polynomial so let's call it q of x with the same properties. So what we do is we take a difference, p of x minus q of x. So it's the same polynomial, it's also polynomial of degree at most n. So we can write it just in the polynomial form, so it's coefficient by the xk. So we need to prove that all coefficients are 0. Then we will prove uniqueness. So what we have the p of x minus q of x should be 0 for any x equal xj, right? So because they should give the same value. So what, it means that the polynomial which is gamma k xjk is 0. And we have n plus 1 equations which can be written as in a matrix form. So it will be coefficients which are given by x at 1, x0, x0 square, 0 n, and multiplied by gamma 0, gamma 1, gamma n. So this is gamma. And this will be A. So this is A. And this should be 0. So this is, so from this condition we have to prove that gamma is 0. So we know that gamma is 0. Well, so if the matrix is non-singular, so if the determinant of A is not 0, then we can prove, then we directly get the gamma is 0, which means that P is equal Q. So then it's unique. It proves uniqueness. So we need to check this condition, the determinant of A of this matrix is 0. And this is what's called van der Monde matrix. So it's called this van der Monde matrix. That's the name. So how you prove that determinant is 0 is actually by directly computing this determinant. It's a nice way how you do it is so what you do, you substitute the last row by the row of the variables x, x squared, and so on, and you call it Vn of x, so it will be determinant of this matrix, but the last row you just put x. So determinant of this matrix, and it's of course polynomial, right? So this is a0 plus a1x plus an xn. So this is polynomial. So what we know from this polynomial is that Vn of xj is 0 for j 0, 1 until n minus 1. So whenever you put xj for this coefficient, you have a repeated row, so determinant is 0. Which means that all of them are roots of this polynomial, and these give n roots, so we can factorize this polynomial. We can factorize it. So Vn of x is leading coefficient an by the product by x minus x0 minus x1 to x minus 1. So this is a polynomial, and it remains to find the coefficient of the an. But now, in order to find an, you will see that this main term, it only appears through this coefficient. You see, which will be, for these determinant products, will only be affected by this matrix. Right? So the an, to observe that an is actually determinant of this part. Right? The determinant of this matrix. And this matrix is the same polynomial, but already size smaller, so Vn minus 1, so where you just only repeat everything until n minus 1, and put in the last row with x and n minus 1. So what we have finally that Vn of x is Vn minus 1 xn minus 1. Well, by x minus x0, x minus x n minus 1. Okay, and then remember that determinant of A is just if you put n here. So what you get, the determinant of A is Vn xn, and it is what? It is Vn minus 1 xn minus 1 by all these products, so it will be xn minus x0, xn minus x1, xn minus xn minus 1. Oh. So you see that determinant of A is non-zero if Vn minus 1 xn minus 1 is non-zero. So it's non-zero if this is non-zero, right? So if this is non-zero, because it's exactly the same. And this is non-zero if, and this is non-zero if and only if the previous one is non-zero. But n was taken arbitrarily, so you can continue it by induction. Until 1. Until 0, no. Until 0, 1. 1. So, no, 0. So here we end with n. Yeah, we can go until 0. But this is just 1, right? So non-zero. So determinant. So the matrix A is non-singular, which proves the uniqueness. So this proves that whenever you have n plus 1 points given for your function, you can pass a unique polynomial through these points, and consider this to be. You can consider this to be approximation of your function if it approximates the function at other points as well, right? So it's exactly so what you did, you're giving some points, and you're passing polynomial exactly through these points, and the question whether it's close to the function or not, because function may be something like this, right? So how close? So the error. So now the next step is estimate what is the error of this approximation. And the next, after the next, will be the step how to make this error smaller. The error of interpolation. So we need some estimate for the difference. So how you do it? So let P of x be Lagrange interpolation of a function. So we need irregularity. So let's consider the function at some interval between a and b, and we assume that it has n plus 1 derivatives. So we assume that it's as smooth as needed for essentially, it has the same smoothness as the number of points so a function through the points through these n plus 1 points. So the theorem tells you that there exists, so for any x from the interval, there exists a point psi which depends on x. So there is a point psi such that you can write f of x at this point as a interpolating polynomial and plus something which is directly expressed for this point. So it will be this derivative, n plus 1, so the highest derivative that we have, at the point psi. So the arrow is defined essentially by the n plus first derivative. So the next derivative, so the polynomial has degree up to n. So essentially it can compensate any derivative up to n. So this is next n plus first derivative. And then you take a product with this polynomial x minus xj through all the points and divide by n plus 1 factorial. So this just comes from the derivative. Okay, so there is this formula. So essentially what it means that if you approximate any function through n points by a polynomial which is exactly passing through these points, so your arrow at everywhere will be controlled completely by the next derivative. So if you have control on the next derivative, you know the arrow. So if it is small, this is just some product. So then we know how close our polynomial to the function. And you see that this is very derivative are important. So you already see that if we don't have n plus first derivative, that it means that actually the difference between n of f and p can be huge. So you can just at n plus 1 point they coincide, but outside these points the difference can be huge if there is no enough derivative. So this derivative is crucial. Okay, so the proof. I will give essentially. I will give more or less idea of the proof. So the details you can see in the book, but just to see how it works. Well, there are two cases. The first case is trivial. The first case is when, so if x coincides with some of the points. If x coincides with some of the interpolation points, then f of x is just equal p of x. So that's, this is 0, then this is just, this is true for any xi. So because whenever you substitute exactly the interpolating point, then this is 0 because there is one 0 term here, and they are equal by construction. So this is just trivial. So that means that we should consider the case when x is not any of these points. So x is different. And then what you do is, so the construction is as follows. So we construct a function which will help us to just to find this xi. So we take a function, so we define a function j of new variable t. So we define new variable t, use new variable t, which is a difference between f of t minus p of t. And then there will be part of the function which depends on x. So f of x minus p of x. So it will be, you see, x is considered, x is fixed, so we consider new function as function of t. And this is function difference at x, and then the product t minus xi, x minus xi. So that's such a function. So check that g of at h point xj is 0. And also j is 0 at x. See, so if you substitute xj, so these are equal by construction, and this product will give 0. And if you substitute x, then if you substitute x, and this is 1, and they cancel. So essentially what you do is, we get, so which means that g of t is 0 at t at all points which correspond to the original n plus 1 point and point x. So it means at n plus 1, n plus 2 points. N plus 1 points. And also by construction, so there, we used polynomials and f. No derivative, it means that g is has n plus 1 derivatives. Okay. So now what we, and all these points are different. So now what you do, so you have points like x0, x1, x2, xn, and some place x also. And we have a function j which is 0 at all these points. Not necessarily intersecting, but 0. So what we have is that it means that at each interval between adjacent points, there is a point with derivative equal to 0. So between each point, 2 points, there is some point where derivative equal to 0, which means that we have derivative equal to 0 at n plus 1 different points, so distinct points. And then you can keep going because you have derivative, first derivative at n plus 1 points. That means second derivative is 0 at n distinct points, etc. So you will end up with n plus 1. It equals 0. So at one point. See. At one point, it means at least 1 point can be. So we find the point. We found the point where n plus first derivative is 0, and then let's just compute explicitly this derivative. So we have gn plus 1 psi equals 0. So this is derivative with respect to time. From what? From this expression. So we have differentiate this term, and this term. So it will be f n plus 1 psi minus p n plus 1 psi minus f of x minus p of x. And then there is a derivative from this product. Taken at t equals psi. So what you have with this expression? So first of all, this is 0, because this is polynomial of degree at most n. So n plus first derivative is 0. And here so this is a polynomial of degree n plus 1. So derivative will give you, so this will give you leading coefficient times factorial, right? So it will give you the n plus 1 factorial divided by the product of the denominators. So this is what you get. Okay. So we have let's put everything to the other side. And then express f. Okay, and plus this whole stuff. So this is exactly what we wanted to, our expression from the theorem. This expression. So we found psi, which depends on x, because by construction it was obtained for given x, and which gives this formula. So our final message, which I will not prove today, I will keep this. So we already have this expression here. So let's compute what is the error. So let's compute the difference between the function and its polynomial interpolation with the infinity norm. So it's maximum in the interval. From a difference. And this difference we have, because this is this term. So this is can be bounded by, this coefficient can be estimated by the norm of the derivative, which is maximum of the norm, multiplied by, divided by n plus, this is just constant. And now it should be multiplied by the now we can multiply the maximum of this expression. And maximum of the expression can be written also as a norm, where W is this polynomial. So this is a function, and this is just maximum value in this interval. So what you see is that this is a given, this we don't have access. No? This is a function that we want to approximate. This is just a constant. So what in principle we have, we can control, we can optimize this norm by optimal choice of interpolation points. So this depends on interpolation points. So the question whether if you can choose interpolation points in such a positions in the interval such that you can guarantee the best estimate. So what will be the best? So essentially the idea is that you have a function, you approximate it by a polynomial through this Lagrange approximation. So you need to give n plus 1 points. So what are the best points where you can measure so that you guarantee the best estimate in this way? So this is the next theorem. I will just formulate and then we do it next time. So the minimum of the norm where all these minimum in all these points from the interval AB so let's take so minimum over all points, and let's consider the interval from what is the interval? It must be from -1 to 1, I guess. So of the norm, so minimum of this norm, it's equals to 2 minus n. And it is attained at points when all points xi is are given by this trigonometric expression, cosine to I plus 1 by n plus 1 pi over 2. So it tells you that there is certain positions in the interval where you must put your points in order to minimize the error bound. So this will continue next time.